Hello everyone, welcome back to Introduction to Computational Fluid Dynamics. Today we are going to observe the general behavior of different types of partial differential equations. So in previous sessions we have discussed about various types of partial differential equations. We have classified them into hyperbolic, parabolic and elliptical equations based upon the nature what we predicted using Cramer's method as well as eigenvalue method. So in today's session, we are going to discuss each of them. So why do we first agenda will be why do we care about classification of partial differential equations? What is the significance of that in terms of analysis? And then we come across various behaviors with examples. So the most important aspect of identifying this particular mathematical behavior is to understand how the fluid behaves once it interacts with the disturbance. So each type of equation, whatever we have discussed till now, will exhibit a particular physical behavior of the fluid. So unless we cannot understand the physical behavior of the fluid, we cannot create domain. We cannot create the domain. As we all know that CFD uses numerical methods to solve the partial differential equations. So unless I can't understand the extent to which the disturbance is carried out, disturbance is carried out in the fluid domain, I cannot develop the domain itself for the analysis. So identifying behavior of the fluid is the foundation step to understand the dimensions of your domain, which is purely dependent on the behavior of fluid under the given conditions. So the computational method should be used for solving equations associated with different class. So how do I implement? Is primarily based on the nature. So we'll understand once we proceed to the various steps. So earlier in previous session we have discussed various types of them, that is hyperbolic, parabolic equations, and elliptic equations. Elliptic equations. Hyperbolic, we said that we'll be having two different roots which are real and distinct. Parabolic, we said that we'll be having one root or two roots which are equal. Then elliptic, we said that the roots are complex. So based upon these analogies, let's proceed further. How these two roots are going to influence, what are the examples of this kind of fluid flows, and how we develop the domain for these kind of flows. So we start with first hyperbolic equation, which has two roots, and two roots are real and distinct. So let us start with hyperbolic equations. So for that, let me consider a point P, where P is considered to be the disturbance. So it can be any object in the flowing fluid. So here, if you observe, there are two characteristic curves. As we discussed, two roots. So two characteristic curves. So each curve forms the boundary for the influence. So the disturbance created by point P will be felt only in this region. The disturbance which is created by point P will be felt only in this region. We call it as region of influence. We call it as region of influence. So the behavior of the flow, in this region is purely dependent on the characteristics or influence of this point P. And this region is limited by two zones or two curves. We call them as characteristic curve. The left side we call it as left running characteristic curve. Right side we call it as right characteristic curve. Now, as I said, the region of influence is the region where the effect of disturbance at P is felt. But how the P will be influenced? How P is going to create disturbance? So for that, we have something called as domain of dependence. So this is the region which influence the nature or behavior of the flow at point P. The nature or behavior of point P will be dependent on this region. We call it as domain of dependence. So basically, this P can be anything. It can be any object placed in the flow field. So by the definition of hyperbolic equation or hyperbolic behavior, you have two different routes. That means two different characteristic curves. As mentioned here, we have left running characteristic curve and right running characteristic curve. And the region before that we call it as domain of dependence, and region after that we call it as region of influence. Now here if you observe A and B, this represents the initial data line. Initial data line. And this initial data line is nothing but the reference system for us, where we define the flow parameters. Now moving to next. So these are two routes. So two different characteristic curves, and one, as you see, it is right running and left running curves. To understand this, let's take examples of that. So steady inviscid supersonic flow, unsteady inviscid flow, and three-dimensional steady supersonic flow are the examples of real-time scenarios which exhibit this kind of behavior. For example, let's try to analyze them or compare this hyperbolic equation, the general representation, with the one of the examples, which is steady flow over airfoil or supersonic steady flow over airfoil. So if you compare A and B here, A and B forms the initial data line for this particular flow, and we can observe there is a formation of shock wave on both sides of the airfoil. This is left running wave and this is right running wave. So is it similar to something what we have discussed here? So the region that is presence of this airfoil itself is nothing but your point P, which is the disturbance. Now because of this presence of the airfoil, you can see the formation of shock wave, and this shock wave is nothing but the characteristic curve for the given flow field. So if you observe, the properties at or the properties generated by this point P, that is airfoil, are limited within this zone, are limited within the zones, that is two characteristic curves, which is left running and right running. So when I develop the domain for my hyperbolic equation, I ensure that the domain is very much limited to the zone where we can identify shocks. I can constrain myself to this kind of domain. So this is something which we already discussed in previous sessions about shock fitting and shock capturing. So size of domain and necessity of various parameters of that domain we have already discussed. So if you see, initial data line is very close to the object, and most importantly is that the shock wave separates the uh, initial data with the flow which is influence, or that is region of influence. So your domain of dependence for this kind of problem, this kind of problem can be very small, very small. So reducing your computational effort. So as if I want to increase it, I can increase, but that is unnecessarily going to increase my computational effort, because there are no changes which are observed beyond this point, beyond this particular point where the shock is generated. Before that, the changes are almost negligible, or the influence of the presence of this body cannot be transferred to the free stream. So because of that, we can create, or we can have very small domain, to perform our computational analysis. So which emphasizes largely on the reduction in computational effort if we properly develop our domain. So this is how the understanding of behavior of nature of a particular governing equation can influence your solution. You can reduce number of computations. By that, you can reduce the time consumption, as well as you can improve the quality of your solution by imparting same number of computation in the required zones. Now moving on to parabolic equations. So parabolic equations, as I said, will have one root or two roots which are equal. If you consider it as two roots, then two roots are always equal. So you will be having only one root, and you are going to experience only one characteristic curve which will be defining the boundary, right? So if you observe, this is the simple example of parabolic behavior of fluids. So you can see the upper boundary condition and lower boundary condition, these are known conditions. These are known conditions, and P is the disturbance, just like the previous case, P is the disturbance. And the disturbance P will travel in this region like this uniformly, and the disturbance of P will not be felt here. So there is no region of influence before point P, rather this is very much distributed, unlike your hyperbolic equations. So this is the only characteristic curve you have. So this line, this dotted line at P represents the characteristic curve. So the point P will be influencing total boundary above this region. So this characteristic curve is going to join the complete boundary conditions which are already known to you. And A and C represents the initial data line from where the flow is initiated, or the properties are already known for you. And C and D represents upper boundary condition. A and B represents the lower boundary conditions. These are always known conditions for us. So the most common example for this can be boundary layer flows. So you can correlate this kind of behavior with boundary layer flows. So we can see one characteristic direction, that is only in this direction it is going to move from point P. So the P will be having one curve, that curve will be limiting itself to the boundary conditions. So study boundary layer flows are the best example. Parabolized viscous flows, unsteady thermal conduction equation, that is dou T by dou T is equals to alpha into dou square T by dou x square plus dou square T by dou y square. Is the best example of parabolic equations which we come across in various stages of this course again. So for this, let us consider the example of viscous boundary layer. This is the viscous boundary layer. You can see the imagined point A and B. This is nothing but the characteristic curve for this particular scenario. And the outer edge of boundary is nothing but the end of the boundary layer, and the inner layer is nothing but the surface of body, or we can call it as wall boundary conditions. So the development of viscous behavior or the viscous nature of the fluid inside the boundary layer can be assumed to be the best example of parabolic equations. Best examples of parabolic equations. Since hyperbolic and parabolic, both equations, if we observe, will travel in one direction. The disturbance will always travel in one direction. So this is the region of influence for this case, and for shock waves we have seen that it is the region between the shock waves as the region of influence. If we observe, these will travel only in one direction, that is the downstream. So the solution for these kind of equations can be obtained directly by time marching solutions. The solutions can be directly obtained through time marching solutions. Now coming to next, which is elliptic equations. So elliptic equations are slightly different when compared to these two. The nature of roots is complex. The nature of roots is complex, which emphasizes that the disturbance as well the disturbance, if I create it, unlike the previous cases where my region of influence and domain of dependence both are separated in previous cases. For example, if I take parabolic equation, this is the disturbance, and this region could have been considered as domain of dependence, which is initial data line, and this is a region of influence which can be separated using the characteristic curve. But in case of elliptical equations or elliptic behavior, the domain of dependence and region of influence both coexist. That means if we consider this as that is A, B, C, D as the domain, the presence of the disturbance here will be traveling in all the directions. It might be initial data line, this can be initial data line, this can be initial data line, or this can be initial data line. So identifying the initial data line itself will become very difficult in this particular scenario, as the presence of the disturbance will have influence throughout the domain. Unlike previous cases where it is restricted to fixed region between two curves or two boundaries, now it has become to the complete domain. That is a major aspect or major difference between the previous two equations and the elliptic equation. So the nature of roots are imaginary. So there is no limited region of influence or domain of dependence, rather both propagate everywhere in the direction, in all the direction. So this makes it very difficult to analyze this kind of problems. So here, since the disturbance is traveling before and or throughout the domain, the size of the domain should be slightly larger to accommodate these changes. To accommodate this behavior, the size of the domain should always be large when compared to the actual disturbance. So size of domain will be very much critical for these kind of problems. So the solution must be carried out simultaneously, because the input values can be influenced by the presence of the disturbance, because disturbance is propagating everywhere. So because of that, the solution cannot be a time marching solution, rather it has to be simultaneously carried out, and it requires more iterations when compared to the earlier two natures of equations. These are also called as jury problems because of simultaneous calculations. So examples are steady subsonic flow over objects and incompressible invisible flow over object. This is the example of the elliptic behavior. You can see that disturbance is traveling downwards. This represents the contour of flow field velocity around the airfoil. You can see that the velocity is decreasing in this direction, velocity is changing in this direction, as well as in this direction. So this shows that the presence of the object is felt even the upstream characteristics. So if I have somewhere domain like this, then that domain will be under the influence of the body, so I may not get the solution. Solution might not be possible for my particular scenario. So to avoid that, what I'll do is I'll create small airfoil with very large domain, where the presence of this domain cannot be felt, or this presence of the disturbance is very much negligible. And because of this, I have to apply the simultaneous solution methods. That means solution is carried out simultaneously with boundary conditions specified, as well as the disturbance created due to presence of the object. So with this, we conclude the session. So we have discussed about the hyperbolic equations, then we discussed about elliptical equations and parabolic equations, along with what is the significance of each, how the behavior of them will impact the solution. So what type of approach we have to select? For example, time marching solution for parabolic as well as hyperbolic, and simultaneous solution methods should be applied for elliptic equations because of the complexity of the flow. So with this, we'll conclude the session. Thank you.